my name's Jeff. Today we're going to go over aerodynamics in forward flight. We're going to be following this outline. We'll first talk some basics of aerodynamics, just so we're all on the same sheet of music regarding terminology and concepts. Then we'll talk about effective translational lift. Next we'll discuss transverse flow, then dissymmetry of lift, and then we'll move into a review. So let's get started. First of all, I'd like to bring your attention to the lift formula. We'll need to understand two primary parts of this lift formula today. They all play a part, but primarily today we're going to need to remember that the coefficient of lift is based on an airfoil's angle of attack and its shape, and that the v squared is velocity squared, or the speed at which an airfoil travels through the air. The next thing we need to remember are the four basic forces acting in aerodynamics. Those are lift versus weight and thrust versus drag. Understanding the four basics of the aerodynamic forces, we know that one is drag. The difference between a hover and forward flight is that in forward flight, our aircraft experiences parasite drag, or drag that occurs from non-lift producing surfaces. Just a quick diagram, parts 1, 2, and 3 here. 1, aircraft in a hover. 2, rotor disc tilted forward, aircraft not moving. Still no parasite drag because the aircraft hasn't started its forward movement yet. Once the aircraft starts its forward movement through the air and has forward flight, it is now experiencing parasite drag. So, we think back to the four forces. We have lift, the vertical component, versus weight, and then thrust overcoming drag. As the aircraft starts to move forward, if everything is in equilibrium, we will not be climbing, we won't be descending. We will be moving forward at a constant speed, and everything will be in equilibrium. The same in a hover. If we had everything in equilibrium, we would be in a stable hover. But of course, as we all know, things aren't always equal. They're not always that simple. So let's move into what things change as we move into forward flight. The first is we start to move through what's called translational lift. So translational lift is, in effect, the rotor system becoming more efficient due to forward movement through the air.
So here we see a diagram showing the effects of induced flow on the angle of attack. The yellow line represents the chord line of the airfoil, and the difference between that and the relative wind, that angle, is the blade angle, or the angle of incidence. With induced flow, or vertical flow through the rotor system, we end up with a resultant relative wind, and our angle of attack is the difference between that chord line and the resultant relative wind, something less than our angle of incidence, or blade angle.
So the greater the induced flow, the less of an angle of attack we have for any given blade angle. Less performance, less CL. So knowing that, in an IGE hover, less induced flow, more angle of attack, better performance. We have the same thing happening in translational lift. So what happens is, as the rotor disc moves forward in flight, the relative wind, the flow through the rotor system becomes less vertical and more horizontal. As it becomes more horizontal, we have less induced flow, greater angle of attack, the rotor system is more efficient. We come to a point where we reach what's known as effective translational lift, or ETL. Now that ETL happens between about 16 and 24 knots, and it represents a point at which the aircraft has essentially left its vortices behind. It's no longer operating in disturbed air, and the induced flow is reduced. So we have a more efficient rotor system. So the benefits from effective translational lift, or translational lift, are we can carry a greater weight, we can fly at higher altitudes, we can fly at higher density altitudes, and we have a decreased power requirement for the same given conditions. The thing about effective translational lift is, as you might expect, it doesn't occur across the entire rotor system at the same rate time. So what happens is we're moving through effective translational lift, and somewhere around 15 knots, the forward half of the rotor system is experiencing more efficiency than the aft half of the rotor system. You can imagine there's a result. Well, the result is ETL can be felt in the aircraft. There's often a shudder, and people call this riding ETL as they're flying in ETL. And there's also a right rolling moment that occurs as you pass through ETL. And this is known as transverse flow. The reason we end up with that right rolling moment is gyroscopic precession. As we know, if something affects the rotor system, it will take effect 90 degrees later in its action. So the front half of the rotor disc is more efficient, operating in less turbulent air and having a more horizontal flow. That manifests itself 90 degrees later in a counterclockwise rotating rotor system at the left side of the rotor disc, which causes greater efficiency on the left and a right rolling moment. Transverse flow. Again, this happens between 12 and 15 knots in most aircraft, and it is a noticeable shudder and a right roll. The last major aerodynamic force that we need to discuss with regard to forward flight today is dissymmetry of lift. Now, dissymmetry of lift is caused through an effect of the V in the lift formula, or velocity of the rotor system, or the airfoil through the air. So we have, as we know, an advancing and a retreating side of the rotor system. The advancing side in a counterclockwise rotating rotor system would be on the right, and we'll be using that dynamic today. The retreating side would be on the left. So let's take a look at this diagram and talk about this a little more.
In this diagram, the yellow side of the rotor disc represents the advancing side, and the blue represents the retreating side. The assumption in here is that the aircraft is moving forward at 100 knots. With that, if the blade tips are moving at 400 knots, the advancing side will be moving forward at 500 knots, and the retreating side will only be moving forward at 300 knots. That is, the relative wind at the advancing side will be 500 knots, and the relative wind at the retreating side will be 300 knots.
Okay, so if in this case, our advancing side is moving at almost 200 miles an hour faster than our retreating side, and we know that velocity squared is a function within the lift formula. We know that the advancing portion of the rotor system is producing more lift. So if this is our direction of flight, we're producing more lift at point 1 than we are at point 2. Gyroscopic precession dictates that this action and this action will occur 90 degrees later. So we end up with an increase of lift here, lift goes up here, and lift goes down here. Well, that would cause, as we moved faster and faster through the air, that would cause the rotor system to want to pitch back, and that wouldn't be very efficient for flight. So geniuses that design helicopters came up with a system. That system is, in a rigid rotor system, the advancing side is allowed to flap up as the angle of attack increases. So as the helicopter rotor system turns, this side wants to produce more lift, moves faster. As it moves faster through the air, that blade is allowed to pitch up a little bit. At the same time, this blade is allowed to pitch down, which decreases the angle of attack at point 1, while simultaneously increasing the angle of attack at point 2, and balancing out the effects of dissymmetry of lift so we don't have that aft movement of the rotor system. So this would be for a rigid system, and in an articulated system, what we would see is individual blades being able to flap. So we'd have flap hinges, and here we have teetering of the entire system in the rigid system. Okay, so today we've talked about dissymmetry of lift, the advancing half of the rotor system generating more lift than the retreating half due to the velocity portion of the lift formula. We talked about how helicopters are designed and rotor systems are designed to accommodate for that to give us a more level profile. We've also talked about transverse flow. Transverse flow, when the forward half of the rotor system becomes more efficient before the aft half of the rotor system, causing a right rolling moment and some vibrations. We also talked about translational lift and effective translational lift. Effective translational lift occurs about 16 to 24 knots, and as spoken about earlier, transverse flow occurs approximately 12 to 15 knots. We also went over some basics of aerodynamics. We talked about the lift formula, we talked about the 4 basic aerodynamic forces, and we talked about parasite drag as well as aircraft in a state of equilibrium. Thank you very much for your time today. Hope you enjoyed the lesson.